Hi everyone, in this video we're going to start to talk about basic stochastic processes. So we'll define what they are, how we use them, and then we'll do a few problems with a specific type of stochastic process that I mentioned that we would talk about before. So let's start out with why are we talking about stochastic processes, or like sort of where we've come from. So far, what we've done in this course is we've talked about probability distributions about random variables, and those random variables can take on different forms, or they can be different situations. Really, they can be any situation. For a stochastic process, we are going to be interested in a situation where the random variable that we are counting or observing or whatever is taken or observed over time. And it may be the case that previous random variables that we've talked about have been observed or taken, so to speak, over time, but time hasn't been a central part of our analysis. So maybe we've just forgot about the time, or maybe we've averaged over the time, and we, in one way or another, we sort of got rid of that time variable. But in a stochastic process, we are very much interested in time. It plays a sort of central role in what we're doing. And so that's the main difference here between what we've done before and then what we're doing now with the stochastic process. Formally, a stochastic process in which we call usually capital X, and then we have parentheses of t. Okay, so x of t is what I'm going to call it. It's a function. So a fancy way to say a function is it's a mapping. So it maps basically the domain to the range is what any function does. And here the domain and the range are interesting, or more interesting than regular functions. But a stochastic process is a function that maps the outcomes of an experiment to functions of time. Okay. That definition is probably opaque, but it's okay. We can move past it, and you'll live to fight another day, even if you don't fully understand that. Now, x sub t is both the name of the process and the name of the variable observed at time t. So it serves two purposes. Basically, x sub t, you can think of it as it's the random variable observed over time. Okay, don't let this formal definition sort of hold you down. Now, for example, what I could do, or what I could be interested in, is maybe looking at temperature of some sort. Maybe I'm a geologist or geographer. I work in the geoenvironmental sciences department, and I could be interested in measuring temperatures, so on and so forth. And so suppose I measure the noon temperature in Shippensburg every day for a year. Okay. The probability distribution of those temperatures is a function of time. Okay, in a sense, the same probability distribution that I would use in January is not going to be the same probability distribution I use in July. Okay? In a sense, every time that I take that measurement, it's a realization from a probability distribution, or I can use a probability distribution to describe each day. And those distributions, because we know that different months or different times of the year are going to behave differently, every probability distribution is different. And so the distribution of those noon temperatures is a function of time in a sense, because it's not just standalone. we have to keep time in our process or in our minds of thinking about this. So now we have to turn a little bit more theoretical just for a second and talk about a special term that's used in the stochastic process language, or the language around stochastic processes, and that's an ensemble. Okay? And so an ensemble of a stochastic process is the set of all possible realizations, or we can call them functions, that can result from an experiment. Okay, so what this means is that for my example above, I looked at the noon temperature in Shippensburg for every day for a year, and that sort of made up my stochastic process, or rather a realization of it. But in a sense, I could do that every single year, right, that I'm alive, and I'm going to get, in fact, many stochastic processes, or I'm going to get many realizations or functions of it. The weird thing to think about is that there's some overarching process that controls the noon temperature of Shippensburg for every day for a year, but it also, it's like some truth. And then every year, we observe one realization from the truth, in a sense. And so the ensemble is the collection of all possible realizations that can come from that experiment. Okay, and so in a sense, here's a better way to describe it. Okay. And so this is a picture from sort of another setting, and so the lines really have no meaning, but I'm taking observations of a variable. You can think of it as temperature at noon every day for a year. Okay, and I do that once, and that gets me a series of numbers, which are my function. Okay, a line is a function in a sense, and so each of these are functions. And so I have one function, or I can call it a realization, for every year that I do this. Theoretically, there are an infinite number of times I could do that, and thus an infinite number of functions or realizations. The collection of all of those, so all of these lines, and you'll notice the dots to mean that there are a lot of these realizations there. The ensemble is the collection of all of them. And so really I have a sort of a two-dimensional problem here. I have to think about the ensemble, okay, all of them together as one, and then I also have to think about each of the realizations by themselves. And so that leads us to a number of interesting things that we have to consider. And so when we talk about, so that's sort of what a stochastic process is. It's taking observations over time. Really, it's a function of time. And we theoretically have a bunch of them. But we're also interested in properties of this stochastic process. And the first property that I always call a property and that we look at is the mean or the average. And so the question becomes, what is the mean, or what is the average of a stochastic process? And you have to think about, when you ask that question, what does the mean mean? So we have a two-dimensional problem, as I mentioned not long before. If I go back here, we've got the ensemble as a dimension, and then sort of each individual realization as a dimension. And that leads us to having two different kinds of averages. And so the first is an ensemble average. And so it means the average value over all possible realizations / functions for a fixed time point t. So that means it's going to take, if you think back to that picture I showed not long ago, it's sort of stopping each realization at the same time point, t naught. Okay, t sub 0 there, which I'll call t naught. It's stopping at that point, and then it's saying what are the average of all of those points. Okay, and then we also have a time average, and that means that the average, that means it's an average over one specific realization or function. So it's sort of an average over time. And so we've got an average over the ensemble average, and then an average over time, which is the time average. So as an example, I could be measuring the temperature of the surface of a space shuttle during a launch, in kelvins. Okay, and so as this space shuttle launches, I keep track of the temperature continuously over the time. Okay, and so the ensemble, or an example of an ensemble average, would be this. So it would say the average temperature of the space shuttle at 30.5 seconds into the launch is 30 Kelvin. Okay. And the time average of an example of a time average for this situation would be that the average temperature of the of the space shuttle during its launch on September 6, 1951 was 38.5 Kelvin. Okay, now that might have been a little vague, and I did that on purpose. Maybe not the example, but when I explained the two averages, because I want you to explore it a little bit by yourself. And so for this first your turn, so in this last example about the temperature on the surface of the space shuttle, I want you to describe, in a sense, theoretically. I'm not, now that looking at that, I don't know if I spelled theoretically right. I want you to describe how I went about calculating those numbers. So for the ensemble average, pictorially even, how did I calculate that number? I didn't actually give you realizations to do, so you can't say what numbers I used, but theoretically, what would I have to do to calculate that number? And in the same way, what did I do to calculate the second number? I know this is a sort of a weird your turn, but think about it. We'll discuss it in class, and hopefully it'll make it a little more clear, less opaque. Okay, so that's it for this video. I'll see you next time for more discussion on stochastic processes.